The results from the experiments in the previous videos of this series, this one and this one, is that the limitation in my experiments is due to noise in the crystals of the notch filter. The notch filter operates at about 10 times higher power than the crystals in the oscillator. So 10 times more crystals would be needed if operated at the same impedance. What I can understand is that firstly, 1 watt is 7 volts and 0.14 amps. That's at 50 ohms. The maximum current per crystal is 10 milliamps peak to peak, which is 3.5 milliamps RMS. I would need 40 crystals in parallel at 50 ohms. Doesn't seem very compatible with the resources at my hand. So I use a 3-to-1 transformer to make 1 watt 21.2 volts and 0.047 amps. That is at 450 ohms. 13 crystals will be enough. 3.6 milliamps per crystal, and that would be 0.2 milliwatts per crystal. That is 7 dB below the specification, which is 0 dBm. So I hope this will be okay. The drawback of this is that the bandwidth of the notch will be 3 times bigger, so I cannot measure close spaced noise anymore. The previous notch operated at 50 ohms would give me the noise sidebands down to about 2 kHz from the carrier. And now I will be able not to see closer than probably 6 kHz or something like that. These are all my 10 MHz crystals, recovered from various experiments. I have measured frequency and noise maximum current to avoid noise and the resistance of them, and from that I can compute the voltage at which noise starts. And then I select from this table one group of 13 crystals here and another group of 13 crystals here. And I don't want to use those that start to get a problem at a low voltage. This is this column. And I am not using either those that have a very low resistance. They will be valuable for some other purpose. These are the two groups of 13 crystals, A and B, that I have selected to use for the two notches that have 1 watt of power, or rather the current associated with 1 watt of power. The frequencies of the crystals within one group, say this one, differ. This is the frequency separation from some reference. It is 220 Hertz down to 100 Hertz. So it's a frequency difference of about 120 Hertz. As a result, when connecting the two extremes in parallel, what I see is this. It's a double minimum, and that's not what I want. I'm now looking at crystal number 19, and that is the first one in the A series. And I compare it now to number 75, which is the last one, 120 Hertz frequency separation. But I have connected a small inductor in series with that crystal. So when I put that instead here, as happens, I get precisely the same resonance frequency. So now I can connect both these into parallel, like that, and hope to see a nice curve with the parallel resistances of those two. It now says something 6 ohms, but I haven't calibrated this properly, so don't trust the absolute values of the resistance. But it shows that this is the way to compensate for small differences in crystal resonance frequencies. I could have used capacitors, but the only capacitors at appropriate values that I have access to are ceramic capacitors, and they are often noisy, so I don't want to use them. An inductor is perfectly noise-free, so that is safe. These crystals have nearly the same frequency. These other ones need an inductor in series to come with the series resonance on that same frequency. So I have adjusted the coils to make all these 13 resonate at the same place within plus minus 30 hertz or something like that. Here is the selective load for 10 megahertz. There are 13 crystals here, some of them with coils of different size to make them have the series resonance at the same frequency. And then they are tuned with a fixed capacitor here, 200 pf, and this variable capacitor. And then on the other side they are fed with 450 ohms from this 3-to-1 turn transformer. Well, here you can see this one. I want a small leak inductance, so I have pushed copper wires into the holes of the ferrite to fill it with copper completely. Then I have a 50 ohm resistor. 4 50 ohm resistors connected to give 50 ohm, but to tolerate 4 watts. And this coil cancels the parallel capacitance of all the crystal. And here's the schematic diagram. I will have to adjust things when connecting this together with the notches. Probably this resistor has to be increased a little bit because there will be losses from subsequent units. Here is what it looks like. The loss, half a megahertz on either side, is 0.3 decibels. But on the frequency of operation where it should load with 50 ohms, the loss is 3.2 dB. Means this power is split into the 50 ohm resistor of inside the box and the 50 ohm resistor of this network analyzer. Now, this is not the way it will be used. In real life, it will be used with a cable that is a quarter wave, and that will be shorted because there will be a notch there. This will be the high power notch filter. One transformer stepping up from 50 to 450 ohm, connected directly to a second transformer that steps down again to 50 ohms. Performance looks like this. At 10 megahertz here, the loss is half a dB. That's mainly losses in the iron. This iron is not a very high frequency kind of iron, or ferrite. Impedance is close to 50 ohms from 5 megahertz to 25 megahertz. So these transformers are pretty good wideband transformers, and this filling them with copper increases the coupling significantly between primary and secondary. That's essential in this application. These crystals are adjusted to a common resonance frequency, and I have connected them from the 450 ohm point here to a capacitor to ground. And this is what I see now on the network analyzer. This is the capacitive load from the what do you call it? The capacitance of the crystals. I have to balance that by an appropriate inductor. Something like this. Then this is what I see. And there is a resonance here, fairly deep one, and it affects performance several megahertz below the frequency of interest. The origin of that, I short the capacitor to ground, and then you can see it disappears. So this coil is a series resonator with the capacitor, but it doesn't matter. I fine-tuned the inductor for the impedance at plus minus half a megahertz, that is half a megahertz above and half a megahertz below the resonance on 10 megahertz to be symmetric. So it's inductive on one side and capacitive on the other. And that is without a cable connected on the output from the notch. Connecting, so I see transmission, we can see that the loss is maybe 0.7 dB or something of that order. I don't remember if I really calibrated it this time. Anyway, this is what it looks like. And impedance is close to 50 ohms, half a megahertz on either side. Now I have connected the selective load, this box, through a quarter wave cable to this notch filter. And then I look at what I have. Firstly, the impedance is close to 50 ohms over the entire range that I'm looking at. It's plus minus 500 kilohertz. The useful bandwidth for me to measure sideband noise is between the 3 dB points of the notch. It is 2 and 3. 3 dB below the attenuation I have 500 kilohertz away. And that is something like 8 kilohertz. It says 7 here, but I have to look more carefully later on. A close range view, I'm sweeping 10 kilohertz. I can see that the notch is 53 dB deep and the impedance is very close to 50 ohms. And that will be for the carrier under test. I have added a means of cancelling the signal at the bottom of the notch. 1 nanofarad to in series with these maybe 400 PF that are in parallel with the tunable capacitor. And from that an inductor and then a capacitor to ground. That is to introduce a variable phase shift. And then the wire goes through 2 ferrite cores that couple to the current. The inductance of these cores is small compared to the impedance we have at this point, which is 450 ohms. And then at the end of the wire, a capacitor to ground. And you can see the capacitor values are small. This way I can get the notch very deep. I'm running the vacuum tube amplifier as an oscillator. Output input, this is the limited output. And the switch is set for the 2-section crystal filter. A 3 dB attenuator and then the stepped attenuator. Into the selective load, a quarter wave cable, and then the notch. And after that, the low noise amplifier here. And this is what I see on the parsers. And you can see clearly here I introduced some instability. I don't know why, but I tried to knock at the oscillator and that fixed it for now. So I have to look for whatever problems could be there. The bad connectors, for example. Well, this is the level that should be there when things are stable. And I switch off the signal by making the stepped attenuator very large. And I bring the signal back. So here is the difference with a large attenuator setting. Here the level is minus 2.2, and when the oscillator is running I have plus 0.5. That is a 2.7 dB difference, but I can clearly see there is a stability problem in the oscillator. But to start with, I want to know approximately what level this corresponds to. Now I have connected a noise head instead of the power from the tube oscillator. At this point there is plus 27 dBm, and now I want to find what is the noise floor. And I have set the S-meter to show 0, and then I switch on the power to the noise head. And I set the current to read a 3 dB increase to within 0.03 dB. And then the noise figure I find is 8.2 dB. That means that the noise floor of the sideband noise is 7.6 decibels above minus 174 dBm per hertz. That gives me a sideband noise level of minus 193 dBc per hertz. There is a problem, however, a measurement issue. This is the impedance that was seen by the low noise amplifier, and the marker here shows that the impedance was 40 ohm and minus 28. That is 500 pf. So I put a matchbox in front of the low noise amplifier to make it see 50 ohms, because otherwise, assuming that the noise figure is the same as I see with the noise head, is maybe incorrect. This is a pi filter designed as a matchbox at 14 megahertz. So the scales mean nothing, but when I tune it in this situation, I can get an impedance of 50 ohms fairly precisely. So I connect that to the low noise amplifier. Again, a difference of 3 decibels between the noise floor with the cold noise head and with current on it. And the indicated noise figure is now 9.5 dB. So it changed by 1.3 dB. The sideband noise now 50 kilohertz away from the carrier, is 1.8 dB above the noise floor. That means 1.8 dB above minus 174 plus, what was it, 9.2 I think, I remember the noise figure. The result is clearly a little bit different, but I have stability problems, and I had another problem, if you see here, while looking at the main screen. What I have done is to hold my hand above this box. It needs to be screened probably, and above the other one it's even more sensitive, and I remove my hand. So I will make the boxes RF tight and try to find the reason for the instability that I see. This is a bandpass filter with the notch at minus 50 kilohertz. It looks like this. Well, measurement tool. Like this. So it doesn't have much attenuation for the strong signal, but it does not let the sidebands at 50 kilohertz through. The impedance at 10 megahertz, marker 10, is very close to 50 ohms. So this does no harm to the strong signal, but it removes the noise sidebands. Now I have a situation with an unstable signal. So I connect the notch filter for a 50 kilohertz notch between the signal source and the measurement system. And it's immediately clear the problem is in the oscillator. And I can switch the oscillator off by disconnecting the feedback loop, for example. And there is a very small difference in the notch. Here is the stability problem. The main reason for it seems to be poor connection in the tube sockets. So I moved the tube a little bit. And then it's good for a while again. I have dipped the tubes in what was it? Polypropylene, and then moved them up and down in the sockets, and things are much better now, but it's not perfect as you have seen. So I will try again and maybe increase the contact pressure a little bit. With some more pressure on the contacts of the tubes, it seems it is more or less stable. And I find now the noise floor at 1.64, sorry, 1.62 on with the current calibration. And I will now replace this 3 dB attenuator with another one. And now the noise is about 0.1 dB higher. Whether that is significant or not, I don't know. Maybe that's just the difference in how much attenuation these attenuators give. This bunch of cables give quite accurately 3 decibels of attenuation here on 10 megahertz. And it looks like the noise floor is significantly lower. 1.49. That's 1.5. It's 0.1 dB below the small one and 2.2 dB below the big 3 dB attenuator. I think I'm seeing the noise of the small resistors inside these attenuators. The noise floor also looks more stable, and if I measure it on different parts or in time, I see very similar values. Well, here's some instability. Of course, instabilities can occur in resistors, that means attenuators, connectors, and of course also in the oscillator and mainly the tube sockets.